Since the dawn of civilization, humans have been fascinated by the passage of time. Our ancestors noticed the rhythmic cycles of day and night, the changing seasons, and the movement of celestial bodies. These observations sparked a fundamental question: how can we measure and understand time? This curiosity led to the birth of timekeeping, a journey that would shape science, society, and technology. In this documentary, we'll explore how humans discovered the concept of measuring time and how clocks evolved from simple observations to ultra-precise atomic systems. Let's begin by stepping back into the ancient world where the first seeds of time measurement were sown. Early humans relied on natural phenomena to mark the passage of time. The rising and setting of the sun, the lengthening and shortening of shadows, and the phases of the moon all provided clues. These cycles were not just practical, they were essential for survival, guiding hunting, farming, and migration. By observing the sky, people began to recognize patterns, leading to the first calendars and rituals. The concept of time was rooted in nature, and every day was a lesson in cosmic rhythm. This foundational understanding paved the way for more structured methods of timekeeping. Sun's movement across the sky became humanity's first clock. By tracking the position of the sun and the length of shadows, ancient people could estimate the time of day. This method was simple yet effective, allowing communities to coordinate activities and rituals. The shadow cast by a stick or stone became a primitive time marker, and soon these observations evolved into more sophisticated instruments. The reliance on sunlight, however, meant that timekeeping was limited to clear days and specific locations. Still, the sun's role as a natural clock was a crucial step in the evolution of time measurement. Sundials were among the earliest devices created to measure time. By placing a stick known as a gnomon upright in the ground, people could observe the shadow's movement and divide the day into segments. Ancient Egyptians, Greeks, and Romans refined sundial designs, carving hour lines and calibrating them for different latitudes. Sundials became symbols of scientific progress, adorning temples and public spaces. Despite their limitations, such as not working at night or during cloudy weather, sundials represented a leap forward in humanity's quest to quantify time. Their legacy endures in modern timekeeping. Civilizations grew. The need for more reliable timekeeping led to the invention of water clocks, or clepsydras. These devices measured time by the steady flow of water from one container to another. Unlike sundials, water clocks could operate indoors and at night, making them invaluable for courts, temples, and scientific experiments. Ancient Persians, Greeks, and Chinese developed intricate water clock systems, some with gears and dials to indicate hours. The water clock's ability to measure time continuously marked a significant advancement, laying the groundwork for future mechanical innovations. Regions where water clocks were impractical, candle clocks offered an alternative. By marking candles with intervals and observing their burn rate, people could estimate the passage of time. Candle clocks were used in monasteries, homes, and even by travelers. Their simplicity made them accessible, though factors like wind and wax quality affected accuracy. Candle clocks highlight the creativity of early timekeepers, who adapted to local resources and need. These devices remind us that measuring time was not just a scientific pursuit, it was a daily necessity, shaping routines and rituals. Middle Ages saw the rise of mechanical clocks, powered by weights and gears. These clocks represented a major leap in precision and reliability. Monasteries and towns installed large mechanical clocks in towers, regulating daily life and public events. The invention of the escapement mechanism allowed clocks to tick at regular intervals, transforming timekeeping from continuous flow to discrete units. Mechanical clocks became symbols of technological progress, inspiring further innovations in engineering and science. Their impact was profound, influencing everything from religious rituals to economic activity. Escapement mechanism is the heart of mechanical clocks. It controls the release of energy from the weights or springs, allowing the gears to move in precise steps. This innovation enabled clocks to tick at regular intervals, dividing time into seconds and minutes. The escapement's rhythmic motion became a metaphor for the heartbeat of civilization, synchronizing communities and industry. Understanding escapement is key to appreciating the engineering behind early clocks, and how this simple yet ingenious device paved the way for more accurate timekeeping. The 17th century, the invention of the pendulum clock revolutionized timekeeping. Dutch scientist Christian Huygens discovered that a swinging pendulum could regulate a clock's movement with remarkable accuracy. Pendulum clocks reduced errors from minutes to seconds, making them the most precise timekeepers of their era. Their reliability transformed navigation, science, and daily life. The pendulum's steady swing became a symbol of precision, and its principles are still used in modern engineering. Pendulum clocks marked a turning point, ushering in an age of scientific measurement. Development of spring-driven clocks made timekeeping portable. By replacing weights with coiled springs, engineers created smaller, more convenient clocks and watches. This innovation allowed people to carry time with them, transforming personal routines and business practices. Spring-driven mechanisms required careful engineering to maintain accuracy, but their portability made them indispensable. The rise of pocket watches and household clocks democratized time, making it accessible to individuals and families. Spring-driven clocks paved the way for the modern era of personal timekeeping. As clocks became more accurate, societies began to standardize time units. The division of the day into hours, minutes, and seconds allowed for precise coordination of activities. Ancient Babylonians used base 60 mathematics to define these units, a system that persists today. Standardized time enabled trade, science, and navigation, fostering global connections. The creation of calendars and time zones further unified civilizations, making it possible to synchronize events across continents. The standardization of time was a milestone in human progress, shaping the modern world. Calendars emerged as tools to organize and map time over longer periods. By tracking the cycles of the sun, moon, and stars, ancient cultures created calendars to plan agriculture, festivals, and governance. The Gregorian calendar, introduced in the 16th century, corrected errors in earlier systems and became the global standard. Calendars are more than just dates, they are frameworks for civilization, enabling coordination and planning. The evolution of calendars reflects humanity's ongoing quest to understand and manage time. Expansion of railways and telecommunication in the 19th century highlighted the need for standardized time zones. Before time zones, each city kept its own local time, causing confusion and inefficiency. The introduction of time zones synchronized clocks across regions, enabling global trade, travel, and communication. Today, time zones are essential for coordinating everything from business meetings to satellite launches. The creation of time zones was a practical solution to a complex problem, reflecting the interconnectedness of modern civilization. 20th century brought the invention of quartz clocks, which use the vibrations of quartz crystals to keep time. When an electric current passes through a quartz crystal, it oscillates at a precise frequency, driving the clock's hands or digital display. Quartz clocks are far more accurate than mechanical ones, with errors measured in seconds per year. Their reliability made them the standard for homes, offices, and scientific instruments. Quartz technology revolutionized timekeeping, making precise time accessible to everyone. Digital clocks ushered in the electronic era of timekeeping. By using electronic circuits and displays, digital clocks provide instant, easy-to-read time information. They rely on quartz oscillators for accuracy, and their versatility allows integration into computers, smartphones, and appliances. Digital clocks have become ubiquitous, shaping how we interact with time in daily life. Their simplicity and precision reflect the ongoing evolution of timekeeping technology, making time more accessible and understandable than ever before. Atomic clocks represent the pinnacle of timekeeping accuracy. These devices measure time by tracking the vibrations of atoms, typically cesium or rubidium. Atomic clocks are so precise that they lose less than a second in millions of years. Their accuracy is essential for GPS satellites, communication networks, and scientific research. Atomic clocks define the international standard for the second, ensuring global synchronization. The engineering behind atomic clocks is complex, but their impact is profound, powering the infrastructure of modern civilization. Atomic clocks operate by measuring the frequency of electromagnetic radiation emitted by atoms as they change energy states. Cesium atoms are commonly used because their vibrations are highly stable and consistent. A microwave signal is tuned to match the frequency of cesium's atomic transitions, and the clock counts these cycles to define a second. This process ensures unparalleled accuracy, making atomic clocks the foundation of global time standard. Understanding atomic clocks reveals the intersection of physics, engineering, and technology in modern timekeeping. GPS satellites rely on atomic clocks to provide accurate positioning and navigation. Each satellite carries multiple atomic clocks, synchronizing their signals to ensure precise location data. The timing information is transmitted to receivers on Earth, allowing devices to calculate their position within meters. GPS time synchronization is critical for transportation, communication, and scientific research. The integration of atomic clocks into satellite systems demonstrates the importance of precise timekeeping in modern technology. Atomic clocks also power global banking and communication networks. Financial transactions, data transfers, and internet operations depend on synchronized time to ensure accuracy and security. Atomic clocks provide the reference signals that coordinate these systems, preventing errors and fraud. The reliability of atomic timekeeping is essential for the functioning of modern infrastructure, from stock exchanges to cloud computing. Without atomic clocks, the digital world would be chaotic and unreliable. Modern smartphones can display ultra-accurate global time instantly, thanks to atomic clocks and internet synchronization. Devices connect to time servers that reference atomic standards, updating their clocks automatically. This seamless integration allows users to coordinate across time zones, schedule events, and access services with confidence. The engineering behind smartphone timekeeping involves complex algorithms, network protocols, and hardware design. Smartphones exemplify how advanced timekeeping technology is woven into everyday life. Hidden engineering behind clocks involves gears, escapements, and oscillations. Gears transmit energy and regulate movement, while escapements control the release of energy. Oscillators, such as pendulums or quartz crystals, provide the rhythmic motion needed for accurate timekeeping. These components work together to divide time into precise units, ensuring reliability and consistency. Understanding the mechanics of clocks reveals the ingenuity of engineers who transformed simple materials into sophisticated instruments. Quartz crystals are at the heart of modern electronic clocks. When voltage is applied, quartz vibrates at a specific frequency, which is used to regulate timekeeping circuits. The stability and consistency of quartz oscillations make them ideal for clocks, watches, and computers. Frequency control is essential for synchronizing devices and ensuring accurate time measurement. The use of quartz technology highlights the intersection of physics and engineering in everyday life. International definition of the second is based on atomic vibrations. Specifically, it is defined by the frequency of radiation emitted by cesium atoms during energy transitions. This standard ensures that time is measured consistently worldwide, enabling synchronization across all technologies. atomic vibrations are incredibly stable, making them the ideal reference for timekeeping. The adoption of atomic standards reflects humanity's commitment to precision and reliability in measuring time. Accurate timekeeping is essential for navigation, both on land and at sea. Early explorers used clocks to determine longitude, improving map-making and travel safety. Today, GPS and satellite navigation rely on atomic clocks to provide precise positioning. The relationship between time and navigation underscores the importance of reliable time measurement in advancing exploration and technology. Timekeeping has always been a guiding force, enabling humanity to chart new paths and discover new worlds. Rise of railways in the 19th century demanded precise time coordination. Train schedules, safety systems, and ticketing relied on synchronized clocks. The adoption of standardized time zones and railway clocks transformed industry and commerce, enabling efficient transportation and communication. Timekeeping became a backbone of industrial society, supporting growth and innovation. The legacy of railway time coordination continues to influence modern logistics and infrastructure. Space exploration relies on ultra-precise timekeeping. Satellites, probes, and spacecraft use atomic clocks to synchronize operations and communicate across vast distances. Accurate timing is essential for navigation, data transmission, and scientific experiments. The integration of atomic clocks into space missions demonstrates the critical role of time measurement in advancing our understanding of the universe. As humanity ventures further into space, timekeeping will remain a key enabler of discovery. Internet depends on synchronized time to coordinate data transfers, transactions, and communications. Network time protocols reference atomic clocks, ensuring that servers and devices operate in harmony. Accurate timekeeping prevents errors, enhances security, and supports global connectivity. The role of atomic clocks in internet infrastructure highlights the importance of precision in the digital age. Without synchronized time, the internet would be unreliable and chaotic. Behind every clock lies a world of hidden engineering. From gears and springs to crystals and atoms, timekeeping devices are marvels of design and innovation. Engineers have solved countless challenges to improve accuracy, reliability, and accessibility. The evolution of clock engineering reflects the creativity and determination of generations who sought to master time. Understanding the mechanics and physics behind clocks reveals the depth of human ingenuity. Frequency control is central to modern timekeeping. Oscillators, whether mechanical or electronic, provide the rhythmic motion needed to divide time into units. Engineers use feedback systems to maintain stable frequencies, ensuring consistent time measurement. The science of oscillation and frequency control is foundational to clocks, watches, and computers. This discipline bridges physics, engineering, and technology, enabling the precision we rely on every day. Modern computing infrastructure depends on precise timekeeping. Servers, databases, and cloud systems synchronize their clocks to atomic standards, enabling reliable operations and data integrity. Timestamps are used to track transactions, monitor performance, and secure communications. The integration of atomic time into computing systems ensures that digital processes are coordinated and accurate. Timekeeping is the invisible backbone of the digital world. Optical atomic clocks represent the next frontier in timekeeping. These devices use lasers to measure atomic transitions at higher frequencies, achieving even greater accuracy than traditional atomic clocks. Optical clocks could redefine the second and enable new scientific discoveries. Their precision is essential for advanced navigation, communication, and research. The development of optical atomic clocks reflects humanity's ongoing quest for perfection in measuring time. Quantum timing systems are emerging as the next evolution in time measurement. By harnessing the properties of quantum mechanics, these systems promise unprecedented accuracy and stability. Quantum clocks could revolutionize navigation, communication, and computing, enabling new technologies and applications. The exploration of quantum timing reflects the cutting edge of physics and engineering, pushing the boundaries of what is possible in timekeeping. As humanity explores other planets in deep space, timekeeping will face new challenges. Different planetary rotations, orbital periods, and relativistic effects require innovative solutions. Space navigation depends on ultra-precise clock to synchronize missions and communicate across vast distances. The future of timekeeping in space will involve new standards, technologies, and concepts, reflecting the diversity of environments and the complexity of exploration. Artificial intelligence is increasingly involved in time synchronization. AI algorithms analyze data from atomic clocks, satellites, and networks to optimize timing and coordination. This integration enhances the reliability and efficiency of global systems, from communication to transportation. AI-driven timekeeping represents a new era, where machines collaborate to maintain precision and adapt to changing conditions. The role of AI in time synchronization is just beginning, promising exciting developments in the years ahead. Future civilizations may measure time differently, especially on other planets. Mars, for example, has a day slightly longer than Earth's, requiring new time standards and calendars. Space colonies will develop their own systems to coordinate activities, navigation, and communication. The evolution of timekeeping will continue, adapting to new environments and technologies. Humanity's quest to understand and measure time is endless, reflecting our curiosity and ingenuity. Timekeeping has shaped civilization in countless ways. From agriculture and trade to science and art, the ability to measure and coordinate time has enabled progress and innovation. Clocks are more than just devices, they are symbols of humanity's quest for understanding and mastery. The story of timekeeping is a story of civilization itself, reflecting our values, ambitions, and achievements. Science of timekeeping involves physics, engineering, and mathematics. From the motion of celestial bodies to the vibrations of atoms, time is measured using principles that span the universe. Scientists and engineers continually refine methods and technologies to improve accuracy and reliability. The pursuit of perfect timekeeping drives innovation and discovery, shaping the future of science and technology. Timekeeping has profound impacts on society. It enables coordination, planning, and communication, supporting everything from daily routines to global operations. Accurate time measurement is essential for education, healthcare, transportation, and commerce. The evolution of timekeeping reflects the changing needs and aspirations of humanity, shaping how we live, work, and connect. History of clocks is filled with hidden stories and unsung heroes. Inventors, engineers, and scientists have contributed to the evolution of timekeeping, often overcoming immense challenges. From ancient sundials to modern atomic clocks, each innovation reflects a chapter in humanity's quest to master time. Exploring the hidden history of clocks reveals the depth and diversity of human creativity. Clocks are engineering marvels combining art, science, and technology. The design and construction of timekeeping devices require precision, creativity, and expertise. Engineers continually push the boundaries, developing new materials, mechanisms, and technologies. The marvels of clock engineering inspire admiration and curiosity, reminding us of the power of human ingenuity. Scientific research depends on accurate timekeeping. Experiments, observations, and measurements require precise timing to ensure validity and reproducibility. Atomic clocks enable advanced research in physics, astronomy, and chemistry. The relationship between timekeeping and science is symbiotic, driving progress and discovery. Time is a fundamental dimension shaping our understanding of the universe. Navigation, both ancient and modern, relies on accurate time measurement. Early sailors used clocks to determine longitude, while modern explorers depend on atomic clocks for GPS and space missions. The connection between time and navigation is deep, enabling discovery and exploration. Timekeeping is a guiding force, helping humanity chart new paths and reach new horizons. Beyond science and engineering, time is a philosophical concept. It shapes our perception, experience, and understanding of reality. Philosophers have debated the nature of time for centuries, exploring questions of existence, causality, and change. The study of time bridges science, art, and philosophy, reflecting the complexity and mystery of the universe. Evolution of timekeeping is ongoing. New technologies, discoveries, and challenges drive innovation and progress. As humanity explores new worlds and develops new systems, the measurement of time will continue to adapt and evolve. The story of timekeeping is a story of curiosity, creativity, and ambition. Our quest to understand and master time is never-ending, reflecting the spirit of exploration and discovery. From ancient observations to atomic precision, the journey of timekeeping is a testament to human ingenuity and curiosity. Clocks have evolved from sundials and water clocks to quartz and atomic systems, shaping civilization and technology. The quest to measure time has driven scientific discovery, engineering innovation, and societal progress. As we look to the future, new challenges and opportunities await, promising even greater advancements in timekeeping. The story of time is far from over. Each tick of the clock marks a new chapter in humanity's ongoing exploration.